Hello, welcome back to Algebra of Conic Sections. We're going to conquer the fourth and final conic section, which is called the hyperbola. So we've already covered circles, which is a conic section. We've already covered parabolas and ellipses in previous lessons. So we've conquered 3 of the 4 conic sections. Here we're dealing with the last one. Now, to be honest with you, hyperbolas are a little bit of a tricky animal the first time you learn it, all right, because they look a little bit different than the other conic sections. And also the way in which you graph it is just a little bit different than the other ones. It's not something that's going to be really difficult or impossible for you to learn. I'm just warning you ahead of time that this one might require a little more brain cells here. So what I'm going to do is break it down for you step by step so it's really easy to understand. First thing I want to do before we jump into hyperbola is I want to quickly talk about ellipses one last time, because the equation of a hyperbola is really, really close to the equation of an ellipse, and I need to show you why that's the case. After that, we'll write down the full-blown equations of hyperbolas, and we'll graph a hyperbola so that you'll understand how to do that as well. So I need to review with you. I need you to recall, because by this time you should have already seen this in my previous lessons, we need to recall the ellipse, right? What is an ellipse? All right, well, the reason I'm having you recall that is because the geometric definition of an ellipse is actually really close to the geometric definition of a hyperbola. So we're going to kind of review what we already know so that when we get to what we're doing today, it'll be very easy to understand. So here we have an XY plane, and I'm going to put over here in this XY plane some focus, which we by now, let me draw it down here actually, focus number 1, and an equidistant direction on the other side. I'm going to call this focus number 2. Now, if you remember the definition of an ellipse, we had this thing called a focal radii. Basically, it's telling you that the distance from focus 1 to a point on the ellipse plus distance from that same point to focus number 2 has to be a constant. That constant is what traces out that egg shape of that we call an ellipse. So all you have to do is lock down 2 points, and there is some shape here that I'm going to draw that will make it such that the distance from here to a point on the shape plus this to the same point down to focus number 2 is equal to a constant. And we all know that that equation, that shape of an ellipse looks something like this. Can I draw ellipses? No, I can't draw very well, but you get the idea. The focus 1 and focus 2, you can see it's totally lopsided. It shouldn't be this far over here, but it should be an equal distance from the edge. The top and bottom should cross the y-axis in the same location, and also the crossing points on the x-axis should be the same location. And what we have learned is that if you pick a point on this ellipse, call it P, and it has some coordinates x and y. If we draw a line from focus number 1 up there, and we draw a line from focus number 2 up there, then we define what we call focal radii. This is the focal radius from here to the point on the edge, and here to the point on the edge. If you think about a circle has only one radius to the center of the circle, right? But since we have 2 focuses or foci for an ellipse, we have 2 radii. We call them focal radii. The distance from here to the edge is called a focal radii. And the definition of an ellipse basically says that the distance from that point P to focus number 1, this is not multiplied, this means just the distance here, plus that same distance P down to the other focus, f sub 2, has to equal a constant. So basically, this blue curve is the special shape called an ellipse, so that this plus this is a constant number. Let's say the number is 10 meters or something. So this plus this will be 10. But then if we move the point P down here, it's telling me that this distance here plus this is also 10. If we take a different point over here, this plus this distance is 10. This plus this distance is 10. This plus this plus this, they're all equal to 10. So it's a kind of a more expanded definition than the simple definition of a circle with one center point. All right? And the wording that we used back when we talked about ellipses was we said that it was the sum of focal radii is equal to a constant. This is a focal radius, this is a focal radius, so the sum of the focal radii, that has to be what's constant. If you pick a constant of 10, it's going to give you a certain shape ellipse. If you pick a constant that it has to equal 4, then it'll be a different ellipse. If you pick a constant that has to equal 2.9, then it'll be a different shape ellipse, just like the radius of a circle is what dictates the shape of the circle. Now, just to close the loop a little bit here, when you do all the math behind this, we have derived in the past that the equation of an ellipse looks like this: x squared over a squared plus y squared over b squared is equal to the number 1. And we talked extensively about how this really looks like the equation of a circle when you manipulate it and all that. But basically, you have an x squared plus a y squared. You have these two numbers, a and b, which are squared in the denominators. A and b basically determine the shape and size of the ellipse. They determine if it's stretched horizontally or if it's stretched vertically. Basically, they determine if it's oriented vertically, horizontally, and so on. So that's all review. And the reason why I'm reviewing it is because the equation of a hyperbola is really, really similar to the definition and the equation of an ellipse. So let's go ahead and draw a little divider. We'll leave this up on the board. And now we're going to turn our attention to the concept of a hyperbola. Okay? So instead of just jumping right into it, we do a little bit of a review first, and that's going to make it a lot easier. So let's go ahead and draw another XY plane, same as before. And hopefully, by having this fresh in your mind, you'll see how similar they are. So once again, we have two focuses, or foci, for the hyperbola. I'll try to line this one up. We'll call this, let's put it over here, focus number 1. And then over here, we'll have an equal distance over here. We'll call this focus number 2, like this. All right, so just like similarly to the equation of an ellipse, where we said that the sum of the focal radii has to be a constant, which means this distance plus this distance has to be a constant number, whatever constant number you want. A hyperbola is that instead of the sum of the focal radii as a constant, it's the difference of the focal radii. The subtraction of the two focal radii has to be a number, a constant number. So you might say the difference in focal radii is 2. That's going to give you a certain shape hyperbola, right? The difference in focal radii is 10. That's going to give you a slightly different shape, but it's going to essentially be a hyperbola. So because it's the difference in focal radii, it's going to produce obviously a different shape. And also because of that, the plus sign that we had in the equation of the ellipse for a hyperbola is going to be a minus sign. And that's where the minus sign for the hyperbolas comes from. It comes from the fact that the definition of a hyperbola involves subtraction instead of addition. That's a huge punchline for you to remember. Hyperbolas involve subtraction. So we have two foci here. And I'm telling you that there has to be some shape, I haven't drawn it yet, but there has to be some shape on the board that's going to make it so that the difference in the focal radii is a number. What is that shape? What is that shape? And so what we're going to do is draw that shape. So you're not expected to be born with this knowledge. I'm teaching you as we go here, but after I get the shape on the board, I'll be able to show you and prove to you why it's the case. Well, this is roughly the shape of a hyperbola. It goes in like this, curves down, and goes back out like this. Okay? It looks kind of like a parabola. We'll talk about the differences in a minute. And then you have a mirror image on the other side that goes in like this, kind of goes to a point, and then out like this. Right? So notice a couple of things before we go any farther. Right? The focus is inside, quote unquote, each half of the hyperbola. Just like a parabola has a focus, which sits in the middle, the focus for hyperbolas also sit in the bowl, so to speak. But there's one crucial difference, because these shapes on the board are not parabolas. I know they kind of look like parabolas, but they're not. Notice how this shape, once you get far away from the focus, it's a straight line here. Once it bends around, of course, but once you get out here, it's a straight line. Once you get away from the focus, it's a straight line. Parabolas, they kind of do something similar, but they're more rounded. Parabolas are more rounded, but hyperbolas kind of get towards straight lines much, much faster than parabolas. So they are a different shape entirely. All right? But in both cases, you do have a focus on the inside here. So what we're going to say is that for the definition of a hyperbola, if you were looking into a book, it would say something like this: the set of points, we're going to call them points P, so that the difference between, BET means between, the distance P to two fixed foci is a constant. Notice that in words, this expresses what I've already said. I'm saying the set of points P, so that the difference between the distance on the curve P to two fixed points is a constant, which is the same thing of saying the same thing as saying the difference in the focal radii that I'm going to draw here in a second is a constant. So what I'm trying to say is, if I were to pick, what color I'm going to use? If I were to pick some point P on this parabola, let's pick this guy right here. We're going to call it P. and of course it has some coordinates x, y. There's an infinite number of points in this branch of the parabola, and there's also an infinite number of points on the blue curve in this branch of the parabola. By the way, I said parabola, I'm sorry, hyperbola. The hyperbola always comes in mirror image branches like this. You cannot just really have one side of a hyperbola. They always come in mirror images like this. So you always expect to see one side and always another side, which is a mirror image of it. A parabola is quite different. You expect just to see one half of the shape there. But in this case, if you see one half, you always expect to see a mirror image on the other side. So what we're basically saying is, if I draw a picture, much like here, I drew a line from the focus to a point on the, in that case, the ellipse. Here I'm going to do my best to draw a straight line, probably going to fail, but I'm going to draw a straight line there, and then I draw a line down. Of course, I can't draw the short line straight, sorry about that. I'll draw this one straight as I can to this focus right here. This line is called a focal radius. It's the distance from the focus to a point on the curve. And then this is the distance from the focus number 2 to the point on the curve. And what we're basically saying is what defines the blue curve, which we're calling a hyperbola, is, by definition, the point P, the distance between P and F1, minus the distance P to F2 must be equal to constant. So again, if I pick the constant to be 5, it'll produce a certain shape hyperbola. If I pick this constant to be 29, it'll be a different shape hyperbola. But the point is, the constant is what dictates the exact shape, but the point is, it's the difference of these focal radii instead of the sum of the focal radii. And because of that, the equation that you get that comes out of it is no longer going to have a plus sign there. It's going to have a minus sign. I'm going to show you that in just a minute. So much like we wrote here that we had a sum equal to a constant, we said the sum of focal radii was a constant. Here I'm going to say that this is, for a hyperbola, the difference of focal radii is equal to a constant. Now let me explain what I'm talking about here. Let's put our finger here and put our finger here. Let's say we measure this, and let's say we measure to be a certain number of centimeters. And let's say we measure this, and it also is a certain number of centimeters. All right? If we subtract them, then we're going to get some number. Let's pretend that number is 3. Okay? What I'm saying is the blue curve is a very special shape, so that if I move this point, let's say down here, then I'm going to measure this distance to the point and this distance to the point, and if I subtract those two numbers, I'm going to get the same number. In this case, it would be 3. If I move the point way over here, if I extend this curve to here, then I'm going to measure a longer distance here, of course, but then this distance down here will also be longer. So when I do the subtraction, I will get the same thing, right? If I move my finger any point on this blue curve, even someplace down here, then this distance, of course, is longer. This one's longer, but when I subtract them, I still get 3. No matter where I draw my finger on this blue curve, the shape of the hyperbola is specially calculated so that the difference in those two numbers is always the same number. The constant, whatever the constant is for the hyperbola that you have, that's what it's going to equal. So in this case, it's long minus short, so you're going to get a constant number. But notice we have another side of it. We have this side, right? So let's say we pick the mirror image of this point, which is over here. Okay? Then the distance from P to F1 is going to be a number. And then you're going to have this distance right here. So you can see this is going to be the same as this one was, and this distance down here will be the same as this one because it's a mirror image. So what you'll have, if I use this definition, PF1 minus PF2, that means this distance minus this distance, you're going to get the same number, but it's going to be the negative version of the number. So I lied to you a little bit. When I said PF1 minus PF2 is a constant, I lied to you just a little bit. What I really mean to say is the absolute value of PF1 minus PF2 is a constant. The absolute value is put in place because because I'm defining it as PF1, the distance to focus 1, minus the distance to focus 2. If I pick any of these, then basically you're going to have short minus long, short minus long, short minus long. No matter what you pick, you're going to get negative numbers, the absolute value of which will still give you, let's say we're still talking about 3, it's still going to give you 3. If I pick any of the numbers over here, it'll be long minus short, which will give you 3. So that's why you really end up with 2 halves of the hyperbola, because the definition really involves an absolute value. You're looking for the distance between the focus and the point on the curve, giving you the same number, It doesn't matter what direction it is, if it's negative or positive, you just want to get the same number. If it's a 3, basically you're going to get a plus or a minus 3, depending on how you do the subtraction. So that's the definition. Now for an ellipse, we said we add the focal radii together, we get a constant, it gives us an equation with a plus sign. For a hyperbola, we're saying we subtract the focal radii, and we have an absolute value that gives us 2 branches here, and that has to be a constant. It's the difference of focal radii there. Now we have an equation that looks very similar to the ellipse equation for the hyperbola. And here's what we have here. Notice there's 2 setups here. There's 2 possibilities here. Much like for ellipses and, much like for ellipses, you can have a vertically oriented ellipse, and you can also have a horizontally oriented ellipse. So the same thing is true for a hyperbola. You can have kind of a horizontally oriented hyperbola, and you can also have a vertically oriented hyperbola, and it's going to depend upon the equation that you have. So let's just forget about the bottom for now and only look at the top. We have a horizontal hyperbola centered at 0, 0. That means the middle of both of these curves is at the origin. And the foci are at negative C0 and C0. That just means you have to pick 2 focuses somewhere. We say they're C units away from the center. Plus and minus, symmetric, right? The difference in focal radii is 2a. That just tells you what the definition is. And the reason it's 2a, I'm going to save that for later. We'll do a few problems where we have to use that number, but basically it tells us the difference of focal radii is equal to 2a. And what I'm mostly wanting to draw your attention to is this equation looks exactly like the equation of an ellipse, except we have a minus sign here. Why do you think the minus sign is there? I've already told you. The minus sign is there because the definition of the hyperbola has it being the difference in focal radii being equal to a constant. Whereas for an ellipse, it was the sum. So that is why hyperbolas and ellipses have almost identical equations. I mean, look at this equation. It's x squared over something, y squared over something. You subtract and it equals 1. And for an ellipse, it's almost exactly the same thing, except you have a plus sign here. Once again, in the case of a hyperbola, the a and the b number are going to determine the exact shape of the hyperbola, just like for the case of an ellipse, the a and the b number, once again, also determine the shape of the ellipse. But one thing I want to draw your attention to here, the way that you figure out if the hyperbola is horizontal or vertical has to do with what term is first. Notice there's a positive term. This whole term is a positive, and this whole term is negative because of the negative sign here. If the x squared term is written first, that means it's positive. If it's positive, if the x squared term is positive, that means the focuses lie on the x-axis, and so the hyperbola is lying along the x-axis. If you look down here, for a vertical hyperbola, I'm going to show you why this is the case later, but if the y term is the positive term, notice the y term is positive and the x term is now negative, whatever term is positive, in this case y, determines where the focuses are, in this case along the y-axis, and determines which direction the hyperbola is oriented. So if you're given the equation of a hyperbola, you will automatically know right away if it's a horizontal hyperbola or a vertical hyperbola. If the x term is written first, so it's positive, the hyperbola lies along the x-axis. If the y term is written first, so it's positive, the hyperbola will always lie along the y-axis. Now this little equation I have written here is similar to what we had for the ellipse. That allows us to calculate the location of the focus when we have the a and the b numbers. And it's the same equation as down here. And then we have this other thing called asymptotes. I'm not even going to read it because it's not important right now, but we have these things called hyperbolas have something called an asymptote. Those are basically guidelines, literally dotted lines that we're going to draw when we sketch our hyperbolas to help us figure out how to sketch the hyperbolas. And it has to do with what happens to the curves way out here when they start to bend over and start to go straight. Remember, this is the equation of a line. The b and the a is the slope, and the x means it's just the equation of a line. So what it's telling us is, how do we draw these hyperbolas? How do the straight lines bend over when they get really far away from the origin? So that's what an asymptote is. It's looking at how something behaves when it gets really, really big, right? So what we're going to do when we sketch these things is we're going to show you how to sketch them by looking at what we call the asymptotes. The most important thing, though, that I want to point your attention to is the equations of a hyperbola have a minus sign in the terms, and also if the x is written as the positive term, it's along the x-axis, and if the y is written as the positive term, it's along the y-axis. All right, let me make sure that I have said everything I want to say. So this is the definition of the hyperbola. The way I've drawn it here is a horizontally oriented hyperbola, but you now know you can have vertically oriented hyperbolas as well. The definition is basically just telling you the difference in focal radii has got to be equal to a number, and that gives rise to these special shapes in blue here we call hyperbolas. Now what I would like to do is go ahead and sketch one of these hyperbolas right in this example. So what we want to do is I want to give you the equation of the hyperbola, and we want to talk about how we would go about sketching it. Where are the x-intercepts? Where are the y-intercepts? What are the asymptotes? We're going to talk about all that stuff here in just a second, but keep in mind that even if you don't totally 100% get it on this one example, we have tons of examples coming, and as you do more and more of them, it will become more I guess easier to understand as you go. It might take a few examples, but I think even with this one here, we will get rid of some of the hardship here, and you'll understand a lot about what's going on. So we're going to sketch this hyperbola, and this hyperbola is x squared over 9 minus y squared over 16, and that's equal to 1. We want to sketch it. Now, this does not mean that we're trying to draw a detailed plot of this parabola. It doesn't mean we're trying to make a table of values for all 4 quadrants and make a beautiful graph. It means that we want to get enough confidence to be able to sketch it and make an intelligent sketch. Now, the first thing I want to ask you is this hyperbola horizontally oriented or vertically oriented? And I know a lot of you guys are not sure, because what you're probably doing is you're looking at the numbers on the bottom. The 9 is smaller than the 16, so you're just thinking, because back for ellipses, we had to look at the numbers in the bottom to figure out if the ellipse was horizontal or vertical. But that's not what I told you just a second ago for hyperbolas. I didn't say that you look at the a and b numbers to determine if it's horizontal or vertical. I said if the x term is the positive term, it's a horizontal along the x-axis hyperbola. If the y term is positive, the hyperbola is on the y-axis, and so it's vertical. So when we go back and look at what we have here, we have an x squared term first. It doesn't matter that the 9 is smaller than the 16. Because the x squared term is written as the first term, we know immediately that this is a horizontal hyperbola. Right? So what we're going to do is we're going to draw the hyperbola over here, and we're going to analyze this equation, and as we start to analyze it, we'll go ahead and mark off the information as we understand it. So let's go ahead. I think what we're going to do is on this board up at the top, let's go ahead and draw a really large XY plot. Won't take the entire board, but we want to make it big enough so that nobody has any problem seeing anything. So we have X and Y. We want to draw this hyperbola over here. All right, so the first thing we want to do when we confronted with a new equation, we want to find the x-intercept and the y-intercept. That means I want to figure out where this thing crosses the x-axis, the x-intercept, and where does it cross the y-axis, which means the y-intercept. So we did this exact same thing when we did ellipses, right? So we want to first calculate the x-intercept, right? But before we do that, notice that 9 and 16 are perfect square numbers, so we can rewrite this hyperbola as x squared over 3 squared minus y squared over 4 squared is equal to 1. We'll just kind of keep that in our back pocket as we continue to work the problems. So what we want to do is we want to find the x-intercept. So the x-intercept means where does this hyperbola cross the x-axis? So wherever it crosses, I'm not sure where it crosses, but wherever it does cross, it means the y value is equal to 0. So that means we set y equal to 0 in this equation that we have here. So we're going to set this guy equal to 0. So we have x squared over 3 squared minus 0 squared over 4 squared is equal to 1. We set the y value equal to 0. That means this whole term goes to 0, and ultimately all we have is x squared is equal to 3 squared. Make sure you understand this term drops away completely. So all we have is x squared over 3 squared is equal to 1. I multiply left and right by 3 squared, so it cancels on the left and it shows up on the right. Okay, so we kind of did two little steps there in one. All right, but I think we're far enough along where you can follow that. Then we calculate the values of x. X is equal to plus or minus the square root of 9, which is 3. 3 squared is 9, so I just wrote it there. So x is equal to plus or minus 3. So this means that the x-intercept is going to occur at 3, 0 and negative 3, 0. Because what we found is that when we set y equal to 0, that's the 0 values here, we get a value of 3 and minus 3 for x. So we have figured out right away that if we go over here and say, all right, here's 1, 2, 3, I'm going to put a dot right here, and -1, -2, -3, put a dot right here. And so what we're going to say is 3 and -3. So we know that this hyperbola crosses here and crosses here. All right, but even though I've kind of showed you what these things look like, you know what's more or less going to happen. It has to come in and cross here, and it has to come in and cross here. Ultimately, you're kind of pretending you don't know what it looks like right now. All you know is it crosses that point. So how do we find the y-intercept? Where does it cross the y-axis? Well, you might think about it for a second and say, well, if we know the hyperbola comes in and crosses like this, and we know it comes in and crosses like this, then the curve never crosses the y-axis. So that's kind of that's a little weird. So let's pretend you didn't know that, and let's try to go ahead and figure out the y-intercept by just calculating it. So we're going to find the y-intercept, which means we set the x value equal to 0. All right, so we go to our equation. We set the x value equal to 0, 0 squared over 3 squared, minus y squared over 4 squared is equal to 1. So that means this whole number becomes 0. So what you're going to be left with is negative y squared over 4 squared is equal to 1. Now what we want to do is move the 4 squared over by multiplication. And we also want to get rid of the negative sign. So basically we're going to multiply the left and the right hand side by negative 4 squared. What we'll be left with is y squared is negative 4 squared. Make sure you understand, if I multiply the left by negative 4 squared, the negative times negative makes a positive, and the 4 squares canceled. Multiply the right by negative 4 squared, and there you go. So the y-intercept is plus or minus the square root of negative 16, essentially. Now you know how to take the square root of 16, but because it's negative 16, it's really an imaginary number. It's 4i. The square root of that is not even a real number. So what it's telling you is that when you attempt to define the y-intercept, you don't get a real number. So there is no y-intercept. That's what you're really trying to find out. So you learn from this that there is no y-intercept. In other words, this curve doesn't cross the y-axis at all, which is what you kind of expect, because ahead of time you already know the hyperbola must come in from the left like this, or from the right like this, and you know it must come in from the left like this. So this doesn't cross the y-axis anywhere. It only crosses the x-axis. So you see, we have figured out without doing any graphing that this is a horizontal hyperbola. And notice that because it's horizontal, we know this thing must cross the x-axis somewhere. And where does it cross? The square root of 9. That's where it crosses. If you take the square root of 9, you get plus or minus 3. Those are the crossing points. So the crossing points come as the square root of what's underneath, but you have to look at if it's horizontal or vertical to figure out where it's going to actually cross. In this case, it's horizontal, so we know it crosses right here. There is no y-intercept. All right? So the other thing we want to look at is, what is the symmetry of this thing? We did this kind of argument when we talked about ellipses. We talked about the symmetry. And we know that ellipses are egg-shaped things, and they're symmetric about the y-axis if you fold it over. They're also symmetric about the x-axis if you fold it over, right? And we talked about the reasons why. Now it turns out that hyperbolas are also symmetric about the x and y-axis. In other words, you can take a look at the hyperbola here. If you were to fold it over, it would fold onto itself, so it's symmetric along about the x-axis. And also, if you were to fold it this way, if you take this and fold it like this, it's also symmetric about the y-axis. So hyperbolas, just like ellipses and just like circles, are symmetric along the x and the y-axis. So that means that if you really want to do a detailed plot, just find a few points in quadrant 1, and then these points will be the same ones over here with a negative sign in the x position. And you can map them down here and put negative signs on the y position because it's the same numbers. It's just mapped into the different quadrants. Now, why is it symmetric like that? All right. If you take a look at the equation, x squared over 9, y squared over 16, minus y squared over 16 is equal to 1. The reason it's symmetric is the same reason the ellipse and the circle is symmetric. The x and the y variables are all squared. So all you're caring about is whatever numbers I put in here. When you subtract this term minus this term, you get a 1. But if I change the x value to be a negative version of itself, I'm still going to square it, and I'll still get exactly the same calculation, which is a 1. It'll still be on the hyperbola. If I take the y value that's on the hyperbola and I take the negative version of it and I square that, then I'm still going to get the same number, so the subtraction will still give me 1. So once you figure out the numbers that are on the hyperbola, you can take negative versions of x and y and you're still going to be on the hyperbola because you're squaring everything. That's why they're still on the hyperbola. That means when you reflect the numbers into the other quadrants in the x and y axis, then you're still going to have points that are on the hyperbola. So it's symmetric like that. So we've shown we have an x-intercept in this case. We don't have any y-intercept in this case. And we've proven through thinking about it that these hyperbolas must be symmetric in x and y. Now we need to talk about the concept of the asymptote, right? So far we haven't drawn anything here, but let me show you. I think what I want to do is I'm going to show you the way in which you're supposed to go ahead and graph this hyperbola. And then I think after that, let me think about this for a second. There's a couple of different ways we can do it. Let's go ahead and plot the points, and then we're going to do the asymptote. So let's go ahead and try to put a few points to this guy and see where it sits. Okay. So if we wanted to graph this thing more thoroughly, then we could do a table of values, right? We could solve for y, in other words. All right, so this equation that we have here is x squared over 9 minus y squared over 16, and that's equal to 1. So if we wanted to find a table of values just to get a few points on this hyperbola, then what we could do is solve for y. So we can move this term over, so we'll have negative y squared over 16 is equal to negative x squared over 9 plus 1, okay, plus 1. All right, so all I've done is subtract the x squared over 9, and so I have a negative version of this here. Now I want to solve for y. So what I'm going to do is multiply by 16, and I'm also going to multiply by negative 1. So essentially on the left-hand side, I'm going to be left with, let's do it over here. On the left-hand side, I'm going to be left with y squared, and on the right-hand side, I'm going to have negative 16 multiplied by negative x squared over 9 plus 1. Make sure you understand, if I multiply by negative 16 on the left, the 16s will cancel. The negative times negative will give me positive, so it'll be gone. And on the right, I'll have negative 16 times what I had before here. Okay, so ultimately, let me go ahead and multiply through here, and I'll have y squared is equal to 16 parentheses x squared over 9 plus 1. Essentially, the negative multiplies in here. Actually, I have a little mistake here. The negative sign goes in here, like this. So negative goes to multiply here, negative goes to this guy, giving me a negative right here, and then the 16 sits on the outside. So then, how do I finish solving for y? Let's switch colors, and then we now know that y is going to equal to plus or minus the square root of all this stuff. So it's going to be the square root of 16 times all of this. So 16 x squared over 9 minus 1. X squared over 9 minus 1. Let me catch up to myself here. All right, now I can do a little factoring on the inside. Notice that 16 and 9 are perfect squares. So ultimately, I want to try to pull them out of the square root if I can. So what I'm going to have here is plus or minus. I'm still going to have the square root. I'm going to write this as 16 over 9, parentheses, x squared. Let me just double check myself. Minus 9. Make sure you understand that. Basically, if I multiply this in, I'm going to have 16 over 9 x squared, which is what I would get here. If I multiply this in, the 9s would cancel, leaving me with 16, which is exactly what I get when I multiply through here. So essentially, I'm just factoring out the 9, and then I have to make, the 1/9, and then I have to make that a 9 right there. You always go backwards to check yourself. This times this gives me this times this. This times this, when you cancel the 9, gives me 16, but then the 16 times 1 is 16. So this is the factored form. The reason I'm doing that is because I can now take the square root of 16 over 9. And it's going to be plus or minus 4/3. Then I still have the square root of x squared minus 9. 4/3 x squared minus 9. Now, I'm doing all of this because now I have an equation that I can try to find values. I can try to make a table of values, try to make at least a few points to sketch this thing, right? So let's go over here to the other board and do that really quickly. And let's make a quick table of values to plot this guy. Let's say that I have the x column, and then y is going to be equal to we're just going to pick, it's a plus or minus, but we're just going to pick the positive. 4/3 square root of x squared minus 9, like this. All right. Now we'll pick a few values. We'll say 3, 4, 5, 3, 4, 5, and we'll just skip a number and go to 7. We don't have to put every number in there. We just want a couple of points to try to see the general shape of this curve. If we put a 3 in here, right, then it's going to be 3 squared is 9, and then 9 minus 9 is 0, which square root of 0 is 0, and that makes the whole thing go to 0. If we put a 4 in there and do the subtraction of the square root, we're going to get 3.5. I'm truncating some decimals here. If we put a 5 in there and square it, minus 9, do all this stuff, we're going to get 5.3. Again, truncating some decimals. If we put a 7 in there and square it, minus 9 square root times 4/3, we get an 8.4. So notice that the number 3 is the smallest value I can put in this thing to actually get a real number. If I put a 2 in here, then 2 squared is 4. 4 minus 9 is -5. You take the square root of a negative number, then bam, you don't even have a real number anymore. So the smallest value of x I can even put in this thing is equal to 3, and that's what I have right here. So let's try to sketch this thing. 3, 0 is already on the board. Now I need to say here's 3, here's 4, 5, 6, and 7. And then I need to go 1, 2, 3, 4, 5, 6, 7, 8. I'll try to fit that in there. Okay. So 3, 0. So 4, 3.5. 4, 1, 2, 3.5 is roughly going to be speaking right there. And then 5, 5.3. Here's 5, 1, 2, 3.5. 5.3 is a little bit above this guy. It's hard to say exactly, but something like this. All right. And then 7 and 8.4. This is 7. 1, 2, 3, 4, 5, 6, 7, 8.4 is a little bit above this tick mark right here, which again is kind of hard to draw, but basically something like this. So if you were to connect those dots, you can kind of see what's going on. It's kind of straight, but then it bends over, it goes through this, and it's going to, we already talked about the symmetry. Anything on the top can be mapped down to the bottom. So this thing is going to look something like this. Something like this. And then on the other side, it's going to look similar. Now, these dots here can be mapped to the other side. Remember, the symmetry of it means that since x is squared, if you make negative versions of x and you square it, it's still going to be in the equation. So it's going to, again, go through something like this. Now, I know this is not perfect. It's not a totally symmetric thing, but that's the idea. That's how you really do a detailed graph of a hyperbola. You solve for y and so on. Notice the equation, actually, when we solve for y, we got a plus or minus. So that means there's another equation with a minus sign in here for the y values, which basically means if I were to do that, I would have negative values for these, which means I would have all of these dots down here. So, but there's no reason to plot them, because once you get a couple of numbers up here, you can just reflect them down here and reflect them over here, and then you're going to have your plot. Now, nobody really likes doing that process. Nobody likes really sketching all of the plots and making a table of values. Generally, we don't make table of values too much. What we want to do is sketch it. So the most important thing is figuring out where it crosses, where the x-intercept is, or the y-intercept, and then how do we sketch it beyond that? So for that, we need to talk about what we call the asymptotes. Remember, I told you when we first talked about it, I said, here is the equation of the horizontal hyperbola, and it has asymptotes, and I gave you some equation there. I said, forget about it. We'll talk about it later. So here is our opportunity to talk about it now. All right? Well, I think what I want to do is I'm going to show you how you're going to do it yourself. And I think what I'm going to do is, like, when you're doing your homework problems, typically there's a certain way you do it. I'm going to show you that first, and then we're going to dive a level deeper, and I want to show you why it works. So first I'm going to show you what to do, and then I'm going to show you immediately after that why that actually makes sense, or why it actually happens. So, or why it works, I guess I should say. So what you want to do for the asymptotes is you want to make a box. And you're saying, what? Make a box. So I'm going to say, make a box. And what I mean by that is the following thing. The equation of the hyperbola that we're given, the original equation is this one. So what I want to do is take this version, and I want to rewrite it in the 3 squared and the 4 squared version. You'll see why in just a second. So the equation of this hyperbola was actually x squared over 3 squared minus y squared over 4 squared, and that was equal to 1. So what I want to do is make a box. And what I mean by that is you look at the numbers underneath. Remember I told you the numbers underneath on the bottom would determine the shape of the hyperbola. This is how it happens. When you take the square root of 3 squared, you get 3, right? So you make a box with lines x is equal to 3 and x is equal to negative 3. Because underneath the x variable is 3 squared. I take the square root of 3 squared, I get a 3. So I'm going to make a box that has vertical lines, negative 3 and positive 3. And also I'm going to look under the y squared or variable here, and I'm going to get 4 squared. I take the square root of that, I get a 4. So because it's under the y, I'm going to say y is equal to 4 and y is equal to negative 4. So it's very simple. You take the numbers underneath, you take the square root, and you make a box. These are vertical lines, and these are horizontal lines. So on the actual graph here, we're going to do that. So x is equal to 3 and negative 3. These are vertical lines, right? So here is a vertical line at x is equal to 3. So what you do is you draw a vertical line that goes right through this. So that's x is equal to 3. And then over here we have also x is equal to negative 3. So we have a vertical line that goes right down below through this guy. All right, so here we have x is equal to 3, and here we have x is equal to negative 3. These are vertical lines that come directly from the equation. Again, I'm not telling you why this works yet, I'm just telling you this is what you do. I will show you why it works in just a minute. Here are horizontal lines, plus or minus 4. Here's 1, 2, 3, 4, so I draw a horizontal line here at y is equal to positive 4, and then negative 1, negative 2, negative 3, negative 4. Here is another horizontal line at y is equal to negative 4. So you literally make a box. That's why I say make a box. Okay? Now this box actually forms what we call asymptotes. If you remember when we studied rational functions, an asymptote is that dotted line, right? Usually they're vertical or horizontal dotted lines. The function gets really, really, really close to it, but it never touches the asymptote. The asymptote is an imaginary brick wall there that the function can't ever really get to, but it gets infinitely close to it. So you can see what's going on here. You have a dotted line here and a dotted line here. What we're going to do now is I'm going to switch colors. I think I'm going to switch to black. So if I can try to draw, the intersection of these two dotted lines is basically right here, and here is the origin. So what you do, I'm not going to be able to draw a really good straight line, I'm sorry about that, but I'll try to go through this intersection, through the origin, through this intersection, and on out. This black line is called an asymptote. You see how the purple curve never really gets to the black line, and the purple curve never really gets to the black line, but the black line serves as a guide. The function gets infinitely close to that line, but never really ever gets there, okay? And I can do the same thing in this direction if I can draw it, which it might be difficult for me to do. But if I go like this, through this intersection point, through this intersection point, through this intersection point, look at that, I did okay. The black lines form asymptotes, okay? Now, the equation of this asymptote is a line. The equation is, let me just double check myself before I tell you something wrong. The equation of this asymptote is 4/3 x, okay? And the equation of this asymptote is negative 4/3 x. Now, first of all, remember back to what an equation of a line x is. mx plus b, right? mx plus b. So m is the number in front of the x, and b is the y-intercept. So there's no b here at all. That means the y-intercept is 0. It goes right through the origin. This one, there's no y-intercept. It goes right through the origin. This means the slope is 4/3. Positive slope means that this line slopes in a positive direction. This one has a negative slope, but it's exactly the same slope as the other one. It's just negative, which means this one is the same slant, but going the opposite way in the sense of a negative slope. And then the slope of this thing is actually 4/3, which means rise over run. Rise up 4, run over 3, which means rise up 1, 2, 3, 4, run over 1, 2, 3. And I know my tick marks are different sizes, but that's okay. Rise 1, 2, 3, 4, run 1, 2, 3. So that means another point on the line is here, and then also to the origin. So boom, I draw my asymptote line. This one's the same thing here. It's a negative slope, so you can go rise 1, 2, 3, 4. I run in the negative way, 1, 2, 3 to the left, so there's another point, and then boom, there's my other line. So far, I've just told you this is how you sketch hyperbolas. Bottom line is, you first figure out where the x-intercept is. We can read that directly from the equation. We put a dot on the graph. Next, we go back to the equation here. We take the square root of what's under x and we make vertical lines from it. We take the square root of what's under y and we make horizontal lines from it. We draw the horizontal and the vertical lines, and then we draw these asymptotes, these black lines, and then going through this point, we draw a hyperbola that almost gets to those asymptotes, but never quite gets there. If you're ever asked to sketch a hyperbola, that's how you do it. Okay, you have to draw the intercept point, you have to find the equations of the asymptote lines, and then you just draw the curves accordingly. Now, what I want to do at the end of the lesson is explain to you why this happens. In other words, it seems really crazy that what you're doing is just looking at the bottom and making lines. Like, how does that work? I hate it whenever books just tell you to do something and you have no idea why you're doing it, okay? This is why you're doing it. Remember, the equation that we got, that we were given of the ellipse is this. We solve it down to this point, okay? Which is this equation here we use to find a few points on the curve, okay? So what I want to do is I want to start with this as a starting point. I'm going to copy it again. Y is equal to 4/3. Notice the 4/3 is right there, by the way. So that's where it's going to come from. But let's talk about it. 4/3 square root, and I think I need to put a plus or minus in there, actually, because remember, it is a plus or minus. I only chose the positive version to make a few values. Plus or minus 4/3 x squared minus 9. Okay. Now what I want to do to show you, we want to talk about what this function is doing, or what this equation, it's not really a function, it's an equation. What is this equation doing as x gets really, really, really big? As x gets really, really, really big, we know that the curve bends over and it almost gets to that black line, but it never quite gets there. So we want to examine that, and the easiest way to do that is to try to mess around with this x and try to factor it out a little bit. So what I'm going to do is over here, we're going to say that this is equal to plus or minus 4/3. And then underneath the radical, I'm going to draw a big radical here. Underneath the radical, what I'm going to do is factor out an x squared. And I know it looks weird, and you're like, how can you factor out an x squared? But if I factor it out, then I have to have a 1 right here, right? And then I have to have a minus sign. And then I can write this as 9 over x squared. Make sure you understand that. If I take the x squared and multiply it in, I'm going to get x squared. If I multiply here, it's going to cancel with this one, giving me a minus 9. So this is the factored form of this. Now I have two things multiplied, but this is a square. It's x squared. So if I take the square root of x squared, then what really is going to happen is it's going to be y is equal to plus or minus 4/3. Whoops. 4/3. The square root of x squared is going to come out as an x, and then I'm going to have 1 minus 9 over x squared. What I'm saying is that this version of this equation is exactly the same as this one, which is exactly the same as the original one once we solve for y. This is what it looks like. Why do I care that this version is, why did I do that? Why do I care about this? Because I want to figure out what happens to the hyperbola when x gets really, really big. Let's make x 20. You're going to have 9 over 20 squared. That's going to give you kind of a small number. 1 minus a small number is going to be pretty close to 1. Square root of 1 is pretty close to 1, but not quite. But let's make x 1 million. Then I'm going to have 9 over 1,000,000 squared. Then this number is going to be incredibly small. It's going to be so small. It's going to be like 0.000. It's going to have like 1,000,000 zeros and then a 1. So essentially it's going to be 1 minus almost nothing, almost 0. So it's going to essentially be a 1 under here. When x gets really, really big, this whole thing is going to be 1, which I take the square root of, and I still get something really close to 1. So what's going to happen is that this guy, what I'm trying to say, this is close to 1 as x approaches infinity. So what it means is that when x gets really, really, really big, this whole square root doesn't even matter because it becomes 1. So as x gets really, really, really big, the actual hyperbola looks like a line, 4/3 x, positive or negative, 4/3 x, right? As x goes to infinity like this, okay? Because this whole radical essentially goes to 1. So what we have really learned here is that as x approaches infinity, or x approaches negative infinity, what it's saying is that y is approximately equal to plus or minus 4/3 x. And I put approximately equal because what you're doing is you're not saying it's exactly equal to that. You're just saying is if x is equal to 10,000 or x is equal to 10 million or something really, 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 really big, then it looks pretty darn close, like the hyperbola becomes this line or gets really, really close to that line. Okay? And the smaller x gets close to 0, then of course it diverges and it's not approximately equal anymore. But then if you make x negative big, 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 the same thing happens. Because if I make x negative 1 million, then I'm squaring it. So I'm getting the same sort of effect, and I'm going to end up having a negative version here. The negative will go into here, so it'll be a negative 4/3 x. So honestly, the plus minus isn't even necessary here, but anyway, it's instructive to go ahead and leave it there to show you that you're getting two asymptotes out. So when you have x getting really, really big, you're going to get the line being 4/3 x. When x gets really, really big in the negative direction, it's going to be negative 4/3 x. And these are these two asymptotic lines. So then, whenever I did the summary sheet, I said, okay, here's a horizontal hyperbola. This is what it looks like, and the asymptotes are plus or minus b over ax. Basically, you take whatever, if it's b squared, you have to take the square root of it. If it's a squared, you have to take the square root. Whatever numbers are here, you square root them, and you just make a line, b over ax. But the reason that that kind of works, or one additional way to think about it, is because if you make a box like this with vertical lines given by this number and horizontal lines given by this number, then by definition, when you draw your lines through there, you're going to get a line with the right slope. So that's why I say this is the deeper way to look at it. The equation becomes the equation of a line as x becomes really, really, really big. That's what this shows you. But the way that you actually do your homework problems is not quite like that. All you really do is you say, well, okay, this is just take the square root of that, you get a 3. Take the square root of this, you get a 4. I'm going to make 4 lines, and then I'm going to draw. There you go. You can do rise over run. You can write your slopes down, and then you just draw your hyperbola closer and closer and closer to it. Now, I think I have said everything I need to say, but there's a lot to it. There is a lot to it. So ultimately, we started out with the review of an ellipse. We said the sum of these focal radii has to be a constant, which gives us an equation of an ellipse that we've done in the past. But we said there's something called a hyperbola, where the difference in the focal radii is a constant. We put absolute value bars around it because of the negative signs that pop up here, but the difference of them when you take the absolute value has to be a constant. That leads to these blue curves called hyperbolas. And then we talked about what do we do when we have a typical hyperbola? We find the x-intercept, we find the y-intercept, and then we talked about finding these asymptotic lines so we can sketch it. But by and large, at the end of the day, all you're going to do for your homework problems is you're going to be given one of these things, and you're going to know if it's a horizontal parabola. If it is, you just take the square root of this term, and you put a dot here, and you know the hyperbola goes through that dot. Then you make a box. You say, okay, x is equal to 3, negative 3. X is equal to square root of this, 4, negative 4. Bam, bam, draw your asymptotes, and then you draw the line appropriately. That's all you do. But I have to get through all of that math so you'll understand where it's coming from. Now, what I want to do now in the next lesson is we want to derive the equation of this hyperbola to show you that this equation of the hyperbola is actually correct, and that you know where that comes from. And then after that, we're just going to be graphing hyperbolas, getting lots and lots and lots of example practice. So make sure you understand this. Follow me on to the next lesson, and we'll conquer it right now.